It wasn't always this easy getting through the Spokane Street corridor. This major transportation link between West Seattle and the rest of Seattle, Harbor Island and the interstate highway system, had for years been a regional bottleneck, slowing not only commuter and truck traffic, but marine traffic on the Duwamish River. The City of Seattle Engineering Department engaged a team of engineers from 3 design firms to study and evaluate the bottleneck. The team proposed 2 new bridges, a high-level bridge for through traffic and a low-level bridge for local transportation. The high-level bridge was opened to traffic on July 14, 1984. The team would now need to design the low-level bridge. 3 movable designs were considered: vertical lift, bascule, and a third, less common design. The team proposed a bold and new variation on a concept that had been adapted from other types of structures. The first concrete, double-leaf, hydraulically operated swing bridge ever built, and they proposed to build it at the existing site. To open and close the twin 413-foot leaves, they would apply an old technology with a new twist: hydraulics. 9-foot diameter pistons would raise the 7,500-ton leaves 1 inch off their service bearings, and slewing cylinders would rotate them 45 degrees on a pool of oil. There would be several advantages to the design. It could be built in the open position, use the existing alignment, provide more horizontal and vertical clearance, and the cast-in-place concrete box girder design would save money during construction and for long-term maintenance. The concrete surface would also be considerably safer than open steel grating, and the low, graceful soffit curvature would complement the high-level bridge. Federal guidelines required that 2 designs be offered for bid: the concrete bridge and an alternative steel design. Because of the concerns about migrating fish, work in the waterway could only take place during a very limited time period. A sophisticated air curtain system would be used to absorb shock waves created by the demolition charges. Not a single fish was killed. A fishway would be built to help young migrating salmon, and parks would be added on both sides of the waterway. Access would be improved. The huge 413-foot leaves, the heaviest movable spans ever built, would be balanced on top of 42-foot diameter pier houses. Building the piers on steep riverbanks in a seismically active region would require several design innovations. The piers would each need to be supported on 32 3-foot diameter concrete-filled steel pipe piles, driven up to 190 feet through alluvial deposits into glacial till. Piles on the deep side of each pivot pier foundation would have longer, unsupported lengths, creating the potential for instability during an earthquake. Steel isolation sleeves would be developed to distribute the center of rigidity to the same level on each pile, so that each pile would pick up an equal share of the load. The sleeves would support a tremie seal. Separate footings 3 feet above the seals allow the piles and the pier structures to move independently. When closed, the tremendous weight of the leaves is transferred down the pier house walls and into the footings. During openings, the huge load is transferred to the lifting pistons. Lift piston diameter was determined by the largest available seal, 9 feet, but the seal had never been used in both a pressure and friction combination. Huge slewing cylinders rotate the suspended 12 by 30 foot pivot shafts 45 degrees to the full open position. Because of the tremendous weight, tolerances between the two pivot shafts and their guide bearings would be critical to prevent any leaning during slewing. Tolerances came within a few thousandths of an inch, closer than anticipated. There would be 3 hydraulic pumps, 2 working, 1 rotating as a spare. Maintenance and repair access would be important. Openings and hoists were designed to allow for the removal and replacement of each piece of machinery. The twin leaves would need to be designed according to the proximity of the high-level bridge. They would need shorter, deeper tail sections, ballasted for equilibrium. Project engineers were also concerned about getting the tips of the leaves to meet perfectly. In addition, both leaves would be built and poured simultaneously, allowing each segment to be precisely adjusted with its counterpart. Provisions for future adjustment were built in. The bridge would be controlled from a 120-foot tower. Over 2,000 interlocking events would be required for operation, with power supplied by fiber optics routed through the core of the high-level bridge. When leaves were locked together for the first time in mid-June of '91, alignment was nearly perfect. Within 3/8 of an inch vertically, 1/2 inch horizontally. Each leaf has enough torsional stiffness so that locks are only required at the center line. The bridge was put into service on August 9th, 1991. In many ways, the building of the West Seattle Swing Bridge demonstrates that it is possible to design and carry out bold new public works projects in a time of shrinking federal dollars. That it's possible to promote industrial and community development while also helping to protect and enhance the environment. And that people can come up with creative solutions not only for the present, but for a rapidly approaching future.